Hello to everyone, we are Joan from Iñigo, Andreu and Toni Balaguer, and we will now proceed on solving exercise 7.13 from Physics 2 Chapter 7, the time-dependent electromagnetic field. The statement says the following. A solenoid has an inductance of 53 millihenries and a resistance of 0.37 ohms. The solenoid is connected to a battery. Calculate how long will the current take to reach half of its final equilibrium value. Our first step will be to give a brief introduction and context. We are given data for an inductor and a resistor in a circuit, which we suppose to be in series with a battery with a given voltage. Therefore, we are discussing a so-called RL circuit. Let us first recall the magnitudes we will be referring to. The voltage will be represented with a V and the units will be the volt. The current with an I, with ampere as the unit. The inductance with an L, and as a unit we have the Henry. The resistance with an R and ohms as their unit, and time, which will be measured in seconds and be represented by letter T. For this particular problem, we will apply the following electromagnetic equations. Ohm's law, which will relate the voltage, the current, and the resistance, as is written on the board. Then Kirchhoff's voltage law, which will be used to set the differential equation. And finally, Faraday's law applied to inductors, which states that the voltage is minus the self-inductance times the derivative of the current with respect to time, developing from the equality of flux with the production of self-inductance L and current I. Moving clockwise along the circuit, we get a differential equation as voltage minus R times I, which refers to the voltage for the resistor, and minus L times di over dt, which represents the voltage from the inductor. And we equal that to 0, which can be rewritten as the following way. The derivative of I with respect to t plus I over tau equals V over L, where tau is just a constant called time constant, which relates the self-inductance with the resistance. The solution is the following result. The current as a function of time is equal to the voltage over the resistance times 1 minus the exponential of minus time divided by tau. We can analyze the following result in this way. Our current will increase as time goes by, and will find its maximum value, which is the voltage from the battery over the resistance of the resistor, where t equals or tends to infinity, as the exponential of minus infinity is equal to 0. Thus, the graph plotted shows the asymptotical growth of I as a function of time.
Once we have understood the essential concept of the problem, we have to plan the route to the solution. The plan is really simple. First, we'll analyze the statement and extract all the data that will be useful to solve the problem later. Then, we'll use the current equation, extracted from the Kirchhoff laws differentiated, and we'll isolate the unknown, the time in this case. So, reading again the statement, we see that they are giving us the value of the resistance, 0.37 ohms, and the inductance L of the solenoid, which has a value of 53 millihenry, that is 0.053 Henry in the international system. If we're asked to find half of the final equilibrium value, first we should know when we get to the equilibrium value. In a charging RL circuit, the equilibrium is reached when the current has its maximum value. So looking at the current equation, it's easy to see that happens when time is infinity. So this value is the voltage over the resistance. Then, to find half this value, we just have to equal the factor that it's multiplying V over R to 1/2. So, we equal 1 minus the exponential to 0.5. And this means that the exponential must have a value of 0.5. Now we have an exponential equation, which can be solved using logarithms on both sides, and, isolating the time, we get that it is equal to minus logarithm of 0.5 times the time constant. This constant is the induction of the solenoid divided by the resistance of the circuit, both given values in the statement. Therefore, we substitute and find that time equals 0.1 seconds, and that's our final result.
Now, let's discuss and analyze other situations. We could be interested in the evolution of the induced EMF across the same inductor. Here, after closing the switch, the voltage is initially at its max capacity, and it decays to zero as the current increases, or as time goes by, as we can see in the graph. In the exercise, we were asked about the charging circuit, but how much time will it get to discharge the exact same circuit? Our starting point is when the circuit reaches the steady state. Now, at the initial time, the current is at its maximum value. This makes sense, since we come from the previous situation. However, now the current starts to decrease as the energy stored is depleted. This time dependence of the current equals voltage over resistance times the exponential of minus t divided by the time constant, tau. By the formula or the right graphic, it's easy to deduce that the circuit discharges when time tends to infinity.